Okay, let's talk about limits. First, we need to understand what the definition is. And I have here that a limit is a tool we use to describe the behavior of a function as the values of x approach or come closer and closer to some particular number. And so to get us talking about this, let's talk about a basic function here. F of x equals x squared. And we should have an idea of the basic shape of this. It's a quadratic that graphs a parabola. And so there's a couple ways that we can start talking about limits to figure out as we approach, let's say, the value of x equals 2, what the y value becomes. And we could do that with a table, and we can do that with a graph. And so what I'm going to put up here is a table. And so you're used to seeing these as t-charts. I'm going to kind of draw it a little bit differently than we're used to. Perhaps usually you see a vertical column here. I'm going to do a row here horizontally. And if I want x to approach 2, then I can say, well, 1.9 is really close to 2. But I can get even closer, and we know that. So I can try like 1.99. That's even closer to 2. And perhaps I want to get even closer, and you can see I just continue here to add on. And then we can have like what actually happens to the function when x equals 2. And so perhaps I should change some color here. And then I could actually be really close to 2 as well, but on the other side, so we just kind of mirror what you see on the left there. And I'm running out of room, but I could put like a 2.1 here, for example. And this will give us the idea. So what I would do is I would go to my calculator, and assuming that I don't make any errors, I can take some values and plug it in. And in fact, what I may do, just kind of to show you, is let's turn this calculator on. So let's say I go ahead and I put in the function x squared, and then I go and tell my table to ask me what values I want to show up. So I'm going to tell it to ask me for my independent variable, and then I'm going to go ahead and go to my table, and let's say I plug in 1.9. I could of course also go back on my screen and put 1.9 squared. I see that I get the y value as 3.61, and I can do this for 1.99, I can do it for 1.999, and of course we know what 2 squared is. And then we can do this on the other side as well. I think I missed one of them in there. Okay, so I've gone ahead and I have written in exactly what you saw on the screen here, and we know what the value of y is when we square x, right? And so what we're doing is, if I'm going to, let's say, get closer and closer to 2 from the left side, so something smaller than 2, let's write that here. We'll put x approaches 2 from the left. So I'm approaching 2 from the left side. Well, what's the behavior of the function? It looks like as we go from the value of 3.61 to 3.9601 to 3.996, and we can go forward even more, we get closer and closer to the y value of 4. So as x approaches 2 from the left, I get closer and closer to 4. And we can also say the same thing as x approaches 2 from the right. and I'll put that here, x approaches 2 from the right, we see that f of x approaches 4 from both the right and the left. So this table suggests that as x gets closer and closer to 2 from either side, that f of x gets closer and closer to 4. So this isn't surprising. I mean, we actually know, as we have written above, that f of 2 is equal to 4. And by a graph, we would also see this as well. So let's do a quick little graph here. It's not quite calibrated here, so let me see if I can move that over. There we go. And not quite symmetric, but let's put x to be 2. You can see my pen's a little bit off with the calibration. So I would have the ordered pair 2, 4, and again, if I approach from the left, and if I approach from the right, we have that function value gets closer and closer to 4. And so the way that we write this is we say the limit, LIM, as x approaches to, see that little arrow, of our function, which here is x squared, we would say that limit as x approaches 2 of x squared is equal to 4. So now we've defined how to write the limit, and we've discussed that we're going to look from the left and from the right to find that. Okay, so in general, what we're going to write is we're going to say the limit as x approaches some value, let's say a, of our function, we can call it f of x, g of x, p of x, q of x, we're going to say it's equal to L. So this is our general notation. And again, we're determining what our function gets really close to, what value gets close to. It doesn't necessarily attain it, so we're getting closer and closer to x equals a, but not necessarily evaluating at where x equals a for that function. Okay, so now let's take another example. Let's find the limit as x approaches 2 of the function g of x, where g of x is defined as the rational function x cubed minus 2x squared all over x minus 2. So a couple ways that we can do this, and you've already seen it, is we can use a table of values to see what happens as we get closer and closer to the x value of 2. We can use a graph, and I'm also going to suggest that we use some algebra. So part of what we hopefully have done in this course is done a little bit of prerequisite review, and so you can automatically start thinking about things like domain, and in particular with rational functions, we would know that we are really concerned about where there might be a vertical asymptote, and we cannot divide by 0, so you've already kept in mind, hopefully, that x cannot be 2 in our domain, right? So there's actually a vertical asymptote at x equals 2, and we could graph that. So let's kind of approach this from the standpoint of algebraic simplification. And so let's analyze the function. So if I have g of x equals to x cubed minus 2x squared, and I've already noted that x cannot be 2, it's in our domain, what I may begin to do is start factoring. And if I factor out an x squared from the numerator, I'll have the quantity x minus 2 all over x minus 2. I can say, hey, this function behaves a whole lot like x squared, except we have provided that x cannot be 2, because again, we cannot divide by 0. So I can graph this function. we'll see how close we get over here to the, there we go, the pen looks pretty good. Except for right there. And so there's going to be a hole in my graph, right? And so if I start saying, well, there is a vertical asymptote, it is at x equals 2. And I want to talk about taking the limit as x approaches 2. Let's see if I can trace this. I'm going to approach from the left, and as I get closer and closer to 2, it looks like what I would see before. There's that open circle here now at 2, 4. I get closer and closer to the y value 4, and then likewise, if I approach it from the right, it looks like I get really, really close to 4. But again, we can't quite attain it here because we have this vertical asymptote. Our function's not defined. So I'm actually going to introduce some notation here. That means to say that the limit as x approaches 2 from the left can be written as the limit as x approaches 2 from the left, that little minus sign is a superscript, of our function g of x, and we get really, really close to what y value? 4, so that's our left-hand limit, and we would say the limit as x approaches 2 from the right it can be written as the limit as x approaches 2, but this time the superscript is a plus sign. I wish I could make that look a little bit better. Let me see if I can undo that. There we go. This function we're calling g of x. Well, let's take a look at it as I approach from the right. It says, what do I get really, really close to? 4. And it turns out that my function actually is not defined at that point, but the limit still exists. So I would say, therefore, the limit of my function, g of x, as x approaches 2, is the same as the limit as x approaches 2 of the function we talked about before, x squared. It's 4. Okay, you may not see that gap visibly on your calculator if you graphed it, so perhaps that's not the best way for you to try these. Maybe try a table of values, but you can see algebraically that we actually have a limit that exists for this function, and it is 4. All right, now let's say we have a couple of little pieces of a graph here, and I don't even need an ordered or a Cartesian coordinate system, just some ordered pairs to demonstrate this. So let's say that this open circle, where it's not defined, that function is not defined, is at that point 3, 4, and you can see that I have right above that, so at the same x value, 3, we have the point defined, and let's say it was 3, 5. So it's defined there. Using that same terminology and notation that we talked about just a minute ago, we would see that the limit as x approaches 3, and let's say we're going from the left, so that means I'm tracing along this chunk. The limit as x approaches 3 from the left, so with my notation I put the minus sign. It appears that I'm going to get closer and closer and closer to the value of 4. So let's just say this function is f of x. The left-hand limit then is 4. And now I'm going to take and look at the right-hand limit as x approaches 3 from the right. That means I'm looking at this top little piece of the graph, and it says if I come in from the right, for my function f of x, I get closer and closer to the value, y value that is, of 5. So we can actually see that these left and right-hand limits are not the same. I do have that the function is defined at f of 3, right? There's a closed circle at 5, but I can overall say that the limit does not exist for this function, and that's for the reason that the left hand and the right hand is not equal. So if the left-hand side limit does not equal the right-hand side limit, no limit exists. Okay, so you're only going to have a limit that exists if the left-hand limit is the same as the right-hand limit. And you can say I've actually given you one where we really do have a function defined at the x value we're approaching. And that's kind of contrary to that last example that we saw. You would actually write for this example the limit as x approaches 3. So that's talking about, you say, it's assuming that you know to check the left-hand side and the right-hand side of this function does not exist. We write D and E, does not exist. All right, now let's take a look at finding a limit of another function. This time, let's approach -2. So again, there's a difference here between the left-hand limit with the minus sign being a superscript, and then we talking about the negative number 2. So I've got the limit as x approaches the x value of -2 of a function f of x, where I'm going to define f of x to be this rational function, 3x plus 2, all over 2x plus 4. And so one of the key things you might start doing is seeing if you can algebraically manipulate this and simplify it. Doesn't look like I'm able to do that. Things that have already caught my eye though, I've realized what the domain is, and I realize that I have a vertical asymptote, so I'll put v dot a, and that would be wherever that denominator is equal to 0. So it looks like I would have a vertical asymptote at x equals -2. And if you recall your horizontal asymptote rules, that would mean that you're comparing degrees of the numerator and denominator, and they're equal since the degree of the numerator is 1 and the degree of the denominator is 1. They're equal, so it actually states with my horizontal asymptote rules that I have one at y equals 3/2, because it says you take the leading coefficient over the leading coefficient, and that becomes then your horizontal asymptote. And so let's just graph this, and depending on your calculator, you can get a pretty good graph of this one. However, if it's an older model, you may not. So the first thing I do when I graph these functions, I start looking at the vertical asymptotes. I know that there's one at x equals -2, which is actually that x value that we're supposed to be approaching to find our limit. Oops, pop that up. And then I have a horizontal asymptote, just change this to green, at y equals 3/2. Okay. And I could make a t-chart, and I could start doing it that way. I could look at my calculator and just get an idea. But this is saying, if I look at even a table of values, look at my calculator, for the graph, I see something like this. And over here, I'm not going to be able to make a beautiful picture here because I'm not calibrated yet on this. You can see my arrow is not in the right spot. I've got this. And so if I want to take the limit as x approaches -2, remember from that last couple of examples that I'm going to have to look at the left-hand limit. So here I am, I'm taking the limit as x approaches -2 from the left. And so if I approach -2 from the left, what you're going to see is that I actually shoot my function value where it's increasing off to positive infinity. So I'm going to note this as positive infinity. And then if I take the limit as x approaches -2 from the right, so I'm going to get closer and closer to -2 from the right, so I'm looking at this chunk, get closer and closer and closer. Well, it turns out that my y values become more and more negative. It shoots off to negative infinity. So the limit actually doesn't exist, recall, because the left-hand limit does not equal the right-hand limit. So I'm going to note that. All right, those two don't equal each other, so I'm going to write Therefore, the limit as x approaches -2 of my function f does not exist. But I was able to tell about the behavior of my function, and I can do this by a t-chart, a table of values that we come up with either ourselves or by a calculator, or even just looking at my graph. But it is important to note that I can talk about the behavior even if we don't necessarily have a limit value that we are given. It turns out we have all kinds of rules or properties of limits that other mathematicians have come up with and said, hey, you guys can use these make your life easier. So I'm going to open this up, if it allows me to, and perhaps it does not. Okay. And I've got them right here. And so let me zoom out just a hair on this. And because this is a video, you'll be able to pause it, retrieve it. But here we have all the rules for our limits, and this can look quite intimidating at first, but it's basically saying, like, for example, number 4 is talking about rational functions. It's saying, look, if you've got a rational function, you can actually take a look at it as taking the limit as the numerator of this rational function over what you would have for the answer as a limit for the denominator of your rational function. And if you look at some of the other ones, like number 2, it's talking about, well, you've got a polynomial perhaps. You can break that polynomial up into, instead of just taking the limit of the whole thing, but take the limit of individual pieces of the polynomial. And whatever you get for those limits, you would add it up, and that's your answer. So these really are quite intimidating to look at first, but if you're used to reading the generalities of mathematics, this is actually quite a beautiful thing. So I have down here at the bottom, there's 3 ways to find a limit. You can use a table, which we've talked about. You can draw the graph. You can do algebraic simplification. So we've done all of these things so far. So let's just see how we can use this in some coming examples. All right, so one example that would be useful would be like taking the limit as, let's say, x approaches 2 of x squared plus x minus 6. Let's put it all over x minus 2. Hopefully you're already trying to look at it, plug it in, and say, well, what happens if I plug in the function value, or excuse me, when I plug in the x value I'm approaching? Well, I can actually see that, that's not in my domain. But that's okay, we have some techniques. So what if I try to do some algebraic manipulation of this? Perhaps I consider factoring that numerator. And so if I think about 2 things that multiply to -6 but add to 1, this is going to factor into x plus 3 and x minus 2, and it's all over x minus 2. I can see that instead of maybe using that property, if you open back up from a moment ago, it looked like I probably could use what was called rule number 4. I really can't, because I can't have that denominator equaling to 0. So I'm actually going to say, well, this function that I started off with, this rational function, it's going to behave a lot like the function x plus 3, except I know that I do not have the x value of 2 defined. And so what I'm really able to do is take the limit as x approaches 2 of, now what I have, x plus 3. This is just a polynomial. I plug in that x value I'm approaching, right? Plug in 2 here, and I get that my limit is 5. So these properties are actually quite nice. I'm able to do that. So as you start getting into doing more and more examples, the most difficult ones seem to be these rational functions, right? They look like fractions, and those tend to scare students. But I'm going to say that we can in general talk about 3 cases. So let's say a rational function is defined as, let's call it capital R of x, and we'll say it's got f of x in the numerator and g of x in the denominator. The 3 cases would be, let's say x is approaching a value of a for our rational function, and my initial inclination is to plug in that that value of a into the numerator and denominator. Well, if I get some number, it evaluates to a number in the numerator, and it evaluates to a number in the denominator, I can actually tell you that the limit will exist. Okay, I don't know what it is quite yet. I haven't given you an example necessarily at this point, but I can say that there's a limit that exists. Now, what about if I do the limit as x approaches a of this rational function? Again, we're just generalizing it to be f of x over g of x. And when I plug in x equals a, I evaluate the numerator to give me an actual number, but in the denominator, I get 0. Well, the limit doesn't exist. And what's going to turn out is that we may approach, our function may approach positive or negative infinity. And we would actually want to tell that behavior. We aren't going to just write DNE because we are approaching plus or minus infinity. We should be able to determine that. And then the third case, if I am given one of these rational functions, I plug in x equals a to the numerator, so I find like f of a and I find g of a. The numerator might evaluate to 0, then the denominator is going to evaluate to 0 in this case. And here, it's not as definitive. I'm going to say that the limit may or may not exist. We'll have to check. You have to try the limit maybe by simplify. Okay, so let's do some examples. Let's take the limit as x approaches 4, and let's say it's a rational function. I have square root of x minus 2 all over x minus 4. Okay, so as I advised before, rational function, maybe I just try to plug in into the numerator 4 and into the denominator 4. So if I plug in 4 into that numerator, I get square root of 4, which is 2. I get 2 minus 2 is 0. Okay, so I'm saying I get 0, and in the bottom I go 4 minus 4 is 0. And so what this implies from what I've stated above is that it's basically meaningless. May or may not exist. Okay, so my suggestion was to try simplifying. Okay, so if I see a function here with a radical symbol, which is this symbol right here, to simplify, you should try to rationalize. So let's simplify by rationalizing. That's a fancy way of saying let's get rid of that radical symbol. And so this whole time, and I may end up dropping it just for the sake of kind of saving time here, this whole time we are still taking the limit as x approaches 4, but I'm going to algebraically manipulate this, and I may end up leaving off that limit notation in just a moment. Okay, so if we're going to rationalize, what we're trying to do is to get rid of this radical. If I just multiply by its conjugate, so I'm trying to get the radical out of the numerator, I'm going to have to multiply the numerator by square root of x plus 2. And you can't just do that to the numerator, you must do that to the denominator, because here now we're just creatively multiplying this initial rational function by 1, right? Something over itself is 1. And so if you go through this and you do first, outer, inner, last, you FOIL these two binomials together, we can see that kind of a shortcut here, you would be squaring the first term and then squaring the second term, right? If I do first, outer, inner, last, that middle terms, those middle terms are going to cancel out. So I can kind of quickly do that numerator. But here in the denominator, when we're multiplying this out, we're actually going to have to do some work to FOIL. Scroll down. Okay, so just to kind of caution you before you get a little too happy with the algebra, let's kind of do that numerator here. If I square something under a square root, so I'm just getting back x here, I have x minus 4, and then in the denominator, let's just go ahead and rewrite that And again, I've dropped that limit notation just for a moment to do some simplifying, but I really am intending to take the limit as x approaches 4. I can see a nice cancellation, and so my problem really becomes taking the limit as x approaches 4 of this other function. We're saying the square root of x plus 2 in the denominator. So I've got 1 over the square root of x plus 2. Okay, so I've used some properties, I've algebraically manipulated this. Now can I plug in 4 to this function that we're saying our initial function behaves like? And so let's see what happens. I go 1 over the square root of 4 plus 2. Yep, sure enough, I'm going to get 1/4. And so that is my limit as x approaches 4 of this function we started off with. So it looks good. Accidentally hit pause there. You may think that's the case for this one, but remember you have a cubic here on the bottom. So actually the degree of the numerator is 2, the degree of the denominator is 3. So you still have that case where the degree of the numerator is smaller, and so you have a horizontal asymptote at y equals 0. Okay, now you pull out your calculator. And I have, on this one, I have a TI-83, so let's take a look at this. Make sure you know how to type this in there correctly. Okay, if you have an expectation of what it should look like, you'll know immediately if there's something weird. It's kind of nice that I have a TI-83 showing on my screen because you can see it did something funny. In the 83s, it just says, hey, if we have some dots here, it's these pixels, and it's not connecting, I'm just going to connect it for you. But I'm smart enough to know, and you're smart enough to know, that it's connecting these because there's a vertical asymptote. It's just saying, oh, next pixel, let's put it together. So this really does not connect. What's actually occurring is that we are getting really, really close to x equals 1 and going in the negative direction, and then getting really, really close to x equals 1 but shooting in the positive direction. So we're smart enough to know that those graphs actually don't connect as it's showing in that TI-83. If you have an 84 and beyond, you should be in good shape. But this tells me if I look from the left, take the limit as x approaches 1 from the left using that notation, it looks like my function, let's call it f, shoots off to negative infinity. And it looks like as x approaches 1 from the right, tracing it here, my y values shoot off to positive infinity. So I can say that my limit of my function, f, does not exist, but I could tell you that end behavior. All right, these two things do not equal, so the limit does not exist. Okay, the next big thing for us to look at is with these rational functions, taking the limit as x approaches plus or minus infinity. So let's find limits as x approaches positive or negative infinity. And what you're going to find out is that these really follow those horizontal asymptote rules. So let's graph the function 1 over x cubed. So if I go to my calculator on my TI-83 here, it's not going to give me a very good view of it, but I know that I have a vertical asymptote at x equals 0. And for my horizontal asymptote rules, the degree of the numerator is smaller. I also have a horizontal asymptote at y equals 0. and I can do a table of values, but I'm going to see that, and let's do it in blue, that I'm going to get really, really close to that asymptote and to this asymptote. And I'm going to see the same thing here on my not so calibrated graph here, but I think you're getting the point. And so I can tell by the graph that if I ask you to take the limit as x approaches infinity, and so this is the positive x direction, my x's are getting bigger and bigger, I'm tracing my graph as x is going to infinity, and I can see that my graph is getting closer and closer and closer to the y value of 0. And I can also say that as x is approaching negative infinity, so my x values, I'm going to negative infinity, so I'm tracing my graph, it's actually going to get closer and closer to 0. I mean, think about it. If I plug in, let's say, 10,000, I go 1 over 10,000, well, that's a really small number. How about 1 over 1 million? That's even smaller. 1 over 10 million, even smaller. So I get closer and closer to the y value of 0. And it would be the same thing as if I did that in the negative direction. What is 1 divided by negative 10 million or 10,000? And we haven't even talked about even cubing it. So in general, the limit as x approaches infinity, or even negative infinity, so I'm going to put plus or minus infinity, where you have a constant in the numerator, let's call it k, so here k was 1, for example. We have x raised to a power, let's call it n. In general, we're going to get 0 as our answer, just as we've seen here. And so this is going to become important as we start taking the limits as x approaches plus and minus infinity of these rational functions. I can use these horizontal asymptote rules I have to help me, and I can also do a few other things, like dividing everything by the largest power of x in the denominator. Okay, so now let's say I'm trying to find out the limit as x approaches infinity of this rational function given in front of me. I've got x minus 5 all over 3x squared plus 2x plus 2. And what you're going to see is that what's happening to our function is actually going to be dominated by the largest, or the highest, I guess, number or exponent of the numerator and denominator. So we end up really just being dominated, what's going on is being dominated by this right here. But if we look at our rules and properties of limits, what it says is that we can take the limit of these individual pieces, we can break it up into talking about the numerator and the denominator, and we can talk about breaking it up into the sum of whatever's in that numerator and denominator, or even the product. And so you'll see quite a bit of more work when it shows you, like for example, if you're in my math lab and it's showing you how to work this out, you'll see quite a bit more notation than what I'm going to do. But what it turns out is that if I just take the degree, the highest exponent here in the denominator, and I divide everything by that power of x, so I've got the limit now as x approaches infinity, and I take the numerator and each little piece and I divide it by that highest power of x, so I'm dividing now by x squared because that's the largest here, and I take that 5 and I divide it by x squared, and I take every little piece of every little part of this It looks quite a bit more complex, but it's going to help me out. What I'm really doing is applying or taking the limit of each part of these, and again, that's what I'm saying you're going to see when it's explained to you perhaps in my math lab. But you think about plugging in infinity to each one of these little chunks, and so let me just do some simplifying here. So that I can see that I've got now the limit as x approaches infinity. I've got 1 over x minus 5 over x squared. I've got over 3 plus 2 over x plus 2 over x squared. And I'm thinking about me just taking the limit as x approaches infinity of each little piece of this. What we just actually talked about in the last example, as I look at something like this first one, well, that's going to go to 0. And I would be subtracting off 5 divided by something that's taking a really big number and squaring it. So 5 divided by a really big number, well, this is going to go to 0. And then I have that rule where I've got a constant in the numerator again. So this is going to go to 0, and this is going to go to 0. And so what I have then, when I take that limit, is 0 over 3. Well, what does that give me? It gives me 0. Now, if you remember your horizontal asymptote rules would have given me the same thing. I would have just said, oh, the degree of the numerator is smaller than the degree of the denominator, and so I have a horizontal asymptote at y equals 0. Well, that's actually going to end up being what my limit is. So I can use that, and I can prove it here, given these properties of limits. Okay, let's try another one. Let's find the limit as x approaches infinity. And this one's going to look quite a bit uglier. Okay, I can't just plug in infinity right now and go, oh, I feel comfortable. There's not algebra here, some factoring that's going to help me out. I have some horizontal asymptote rules, so if I remember those, I can use them. This says the degrees are equal, so I would use the leading coefficient of the leading coefficient. We just talked about, though, showing our work a little bit with the properties of limits, and so with that, we would say take the highest power in the denominator, and let's divide every term by that. Well, in the denominator we have an x cubed, and so we can divide everything by that x cubed, right? All I'm doing is just rewriting this problem in a different way. Not doing anything weird math-wise. I'm allowed to do this. And then I'm going to simplify. Okay, and so perhaps we rewrite this. We see what we're dealing with. The limit as x goes to infinity. I've got 2, I've got minus 1 over x squared plus 7 over x cubed all over 4 plus 3 over x minus 100 over x cubed. Okay, and remember those properties say I can take and apply the limit to each one of these little pieces. And so you'll see it written out like that if you look up how to do this, maybe in my math lab. But we just had a rule that said, well, this is going to be 1 divided by, or a constant rather, divided by a really big number. Well, that goes to 0. This is going to go to 0. And the same occurs for these other little pieces. And so what you end up with is just that 2 over 4, which simplifies to 1/2, which, as I mentioned, is actually going to correspond to those rules of horizontal asymptotes. One last little one so that I make sure that we've gone through every sort of scenario with these that could be possibly scary. You'd repeat these with the negative infinity as well in a similar fashion. Let's try 5x to the 6th plus 3x all over 2x to the 5th minus x minus 5. So you look at this, and there's, as far as manipulating it just with factoring or something, I'm not going to be able to do that. But again, like I've mentioned, we are really being dominated by these terms here, and so you can really just look at these leading terms, or you can go through and divide everything by this x to the 5th, and perhaps that's what we're more comfortable with at this point. But I think you're getting the overall idea. You'd be able to see that this is going to end up going to 0, to 0, to 0. And so what I'm looking at are these dominating terms, is what I'll call them, just as I mentioned. I've got 5x over 2. And now let's think about what happens if I plug in a really big number in for x. So I'm going to say, like, I'm thinking about infinity here. Well, 5 times a really big number divided by 2 is still a really big number. And so this actually would have the limit as positive infinity. And if you had to plug in negative infinity, well, you'd say, well, 5 times a really big negative number divided by 2 is still a really negative number. So you'd be able to do these examples with positive or negative infinity here. Okay, so this is a pretty lengthy recording. I'm going to go ahead and stop it there, and hope that we've gotten our understanding of limits taken care of.